Hello everyone, today we will learn about the properties of equations and inequalities in the first lesson. In the study of algebra, we go through the process from numbers to equations, and the study of equations includes equations and inequalities. Based on equations and inequalities, we study understanding equations and solving linear inequalities. We also understand that there is an inherent connection between functions and equation inequalities. What is the theoretical basis for solving inequalities? What is the intrinsic relationship between equation inequalities and functions? In this unit, we will continue to delve into the properties of equations and inequalities based on our junior high school studies. In junior high school, we have learned about inequality and inequality. What are the common inequality relationships? Can you express it in written language and symbolic language? The common inequality relationships include greater than, less than, greater than or equal to, or can be expressed as not less than or equal to, or not greater than. Their symbolic language is shown on the right side of the table. With these symbolic languages, can you use inequalities or inequality systems to represent the inequality relationships in the following problems? The first question is about a speed limit of 40 kilometers per hour on a certain road section. This sentence describes the speed limit for vehicles traveling on that road section. Therefore, we can assume that the speed of the cars traveling on this section is v kilometers per hour, and the speed limit of 40 kilometers per hour means that the magnitude of the speed v cannot exceed 40. Since it is also a moving car, the magnitude of v must be greater than 0, so the inequality is 0 less than v less than or equal to 40. Let's take a look at the second question. According to the quality inspection regulations of a certain brand of yogurt, the fat content F in yogurt should not be less than 2.5%, and the protein content P should not be less than 2.3%. The unequal relationship implied in this question is that the fat content F should not be less than 2.5%, and the protein content P should not be less than 2.3%. Thus, we can formulate an inequality system where F is greater than or equal to 2.5% and P is greater than or equal to 2.3%. Next, let's take a look at the third question. The sum of the two sides of a triangle is greater than the third side, and the difference between the two sides is less than the third side. The inequality relationship implied in this question is the three-sided relationship of a triangle. Therefore, we can assume that the three sides of a triangle are A, B, and C. The inequality can be expressed as a plus b is greater than c, and a minus b is less than c. Of course, other reasonable forms of answers are also correct. Okay, let's take a look at the fourth question. Among all the line segments that connect a point outside the line with points on the line, the vertical line segment is the shortest. This question describes a geometric problem, so we can first create a shape based on the meaning of the question, and then find the inequality relationship within it. First, let's draw a straight line AB, as shown in the figure. Let C be any point outside the straight line AB, CD be perpendicular to point D, and E be any point on the straight line AB that is different from point D. Connect the line segment CE. We say that among all the line segments that connect point C outside the straight line to various points on the straight line, this CD is called the vertical line segment, and CE is called the other line segment. Since the problem states that the vertical line segment is the shortest, there is a line segment with CD less than CE. To summarize the above content, how do we use inequalities to express the inequality relationships inherent in practical problems? Firstly, we abstract the inequality relationship from practical problems, and then we use letters to represent the numbers in the inequality relationship. Next, we connect these letters with inequality signs to establish inequalities. This is a process of mathematical abstraction, which is the process of abstracting mathematical models from practical problems. Okay, now we can use inequalities to express inequality relationships. Can this solve practical problems? Let's take a look at the following question. A certain magazine was originally sold at a price of 2.5 yuans per copy, but it can sell 80,000 copies. According to market research, for every 0.1 yuan increase in the unit price of the magazine, sales may decrease by 2,000 copies. How to price it so that the total sales revenue after price increase is not less than 200,000? The inequality relationship implied in this question is that the total sales revenue should not be less than 200,000 yuans, so we should use letters to represent the total sales revenue. The total sales revenue should be equal to the sales unit price multiplied by the sales volume, and according to the proposal, the sales volume is affected by the sales unit price. So we can set the price of each magazine at X yuan after the price increase. How is the sales volume specifically affected by this unit price? Let's read the question. How many units have the sales price increased by 0.1 yuan compared to 2.5 yuans? What about the sales volume? On the basis of 80,000 units, how many units should be reduced by 2,000 units? That is, how many units should be reduced by 2,000 units? So we can express it this way: the sales volume is a multiple of 80,000 copies minus 2,000 copies. Who should this multiple be? It should be the part where the sales unit price X is higher than 2.5, which is several times 0.1. Therefore, the expression for sales volume is as follows: sales volume multiplied by sales unit price is the total sales revenue. Therefore, we only need to multiply this equation by another x to obtain the expression for total sales revenue. According to the proposal, the total sales revenue should not be less than 200,000 yuans, so this equation should be greater than or equal to 20. This is the inequality we have listed. Unfortunately, we cannot solve this inequality. Why do we look at the left side of the inequality and open the parentheses, which will inevitably produce a term such as the square of x? It is not a linear inequality that we have learned before, so if we want to solve this practical problem, we need to study the solutions of other inequalities. So how to solve the inequality? If we want to study the solution of inequalities, we need to analogize the solution of equations. So, what is the main basis for understanding equations? Can you analogize solving equations and find the main basis for solving inequalities? Recalling the process of solving equations in middle school, we often use the operation of converting a coefficient into one, which is called equality property. Therefore, the main basis for solving equations is the properties of equations. Similarly, when it comes to inequalities, the main basis for solving inequalities should be the properties of inequalities. Therefore, it is necessary for us to study the properties of inequalities, continuing to inquire. In order to study the properties of inequalities, we must have the ability to derive new inequalities from known inequalities. So we must compare the size relationship between two equations. So the question arises, how to compare the size relationship between two equations? We know that the letters in the equation are actually real numbers, so the values in the equation are also real numbers. Therefore, when we want to compare the sizes of two equations, we are essentially comparing the sizes of two real numbers. There are basic facts about the comparison of the sizes of real numbers a and b. If a minus b is a positive number, then a is greater than b. If a minus b equals 0, then a equals b. If a minus b is a negative number, then a is less than b, and vice versa. In this fundamental fact, 0 is the boundary between positive and negative numbers, and serves as the benchmark for comparing the size of real numbers. We transform the size relationship of real numbers into studying the sign of their difference. Its essence is to involve operations in the process of size comparison, providing a tool for comparing the size relationship between two real numbers by studying the sign of their difference. This method of comparing sizes is called the difference method. Not only can the ratio be used in two real numbers, but we can also use the difference method for the ratio of two equations. Let's take a look at the following example. Example 1 compares the size relationship between x plus 2 multiplied by x plus 3 and x plus 1 multiplied by x plus 4. To compare the sizes of the two, simply compare the relationship between their difference and 0. So we subtract the two equations. First, we should expand the two equations. The result of the subtracted expansion is x plus 5x plus 6, and the result of the subtracted expansion is x plus 5x plus 4. Both parts have x plus 5x. Subtracting the same terms leaves only a constant, 6 minus 4 equals 2, which is obviously greater than 0. So if the difference between the subtracted equation and the subtracted equation is greater than 0, it means that the subtracted equation is greater than the subtracted equation. Therefore, x plus 2 multiplied by x plus 3 is greater than x plus 1 multiplied by x plus 4. This question is actually a simple application of the difference method. In fact, the difference method still plays a very important role in proving many important unequal relationships. Let's take a look at example 2. The image on the right is the emblem of the 24th International Congress of Mathematicians held in Beijing. The emblem is designed based on the string diagram of ancient Chinese mathematician Zhao Xuang. The brightness of the colors makes it look like a windmill, representing the hospitality of the Chinese people. Can you find some equal and unequal relationships in this diagram? For the convenience of communication and expression, we first abstract this emblem as a planar geometric figure, which can be seen as a square ABCD surrounded by four congruent right-angled triangles with their hypotenuse. We want to find equal or unequal quantity relationships in this planar shape. First, we need to analyze which quantities are present in the planar shape. Common quantities include length, angle, and area. According to our understanding of the shape just now, it is a square surrounded by the hypotenuse of four congruent right-angled triangles. We can start from the area to discover unequal relationships. From the graph, we can also see that the area of squares ABCD is significantly larger than the sum of the areas of the four right-angled triangles. The extra area is obviously the area of the small square GHE and F in the middle, which is the inequality relationship we discovered. If I tell you that the lengths of the two sides of a right triangle are A and B respectively, and A is not equal to B, can you express the discovered inequality relationship in inequality? Firstly, we need to represent the area of a square. The area of squares ABCD should be the square of AB, and AB, as the hypotenuse of a right-angled triangle, should satisfy the Pythagorean theorem. AB should be equal to the sum of A and B at the root. So the area of squares ABCD is A plus B. So the area of each right-angled triangle should be 4 times 1/2 AB. Since there are 4 right-angled triangles, they need to be multiplied by 4. So the sum of the areas of the 4 right-angled triangles should be 4 times 1/2 AB. That is 2 AB. According to the inequality relationship, there is an inequality that the sum of A and B must be greater than 2 AB. We say that the prerequisite for this inequality to hold is that A is not equal to B. What if I change the condition to A equals B? If the two sides of a right triangle are equal, does the inequality A plus B greater than 2 AB still hold? Let's take a look at the diagram. Earlier, we mentioned that the area of squares ABCD is larger than the sum of the areas of the 4 right-angled triangles. The area of the middle square GHE and F is the area of the square GHE and F. The side length of this square is GH, which should be the absolute value of A minus B. When A equals B, the absolute value of A minus B is 0, so the side length of this square is 0. Therefore, squares GHE and F will be reduced to 1 point. At this point, the area of square ABCD and the sum of the areas of these 4 right-angled triangles should be equal ... So the inequality becomes an equation where A plus B equals 2 AB. To summarize our research process, A and B are the right-angled side lengths of a right-angled triangle, which should be positive real numbers. The inequality relationship satisfied by A and B is that the sum of A and B is greater than or equal to 2 AB. Can this conclusion be extended to all real numbers? That is to say, if any AB belongs to R and the sum of A and B is greater than or equal to 2 AB, does this conjecture hold? Please prove or falsify using algebraic methods. At this moment, we obviously need to compare the size relationship between A, B, and 2 AB, so we naturally need to make a difference. The result of subtraction is the complete square of A minus B, which is greater than or equal to 0. Therefore, we can conclude that the sum of A and B should be greater than or equal to 2 AB, and the equal sign holds only when A equals B. What does it mean to be and only B? We can understand it as a necessary and sufficient condition, which means that in the inequality A plus B is greater than or equal to 2 AB, the necessary and sufficient condition for this equal sign to hold is that when A and B are equal. We take the equal sign here. A must have B, and A must be equal to B. This is the meaning of if and only if. So the above inequality is called an important inequality. Finally, we will summarize. In this class, we first reviewed how to abstract inequalities from the unequal relationships contained in practical problems. This is a mathematical abstraction process, which is the process of abstracting mathematical models from practical problems. Secondly, we have learned the basic facts of the size relationship between two real numbers. Its essence is to involve operations in the process of size comparison, transforming the problem of the size relationship between two real numbers into a problem of their difference sign. This method of comparing sizes is called differencing. The difference method can also be used to compare the size between two equations, which lays a theoretical foundation for the inequality properties we will study next. So what are the properties of inequalities? How can we study these properties? Please refer to the second section on the properties of equality and inequality.